All right, so we're looking at page 2 of exam 1 here for the summer semester. Um, so let's take a look at question number 5. So it asks which molecules are polar, right? Then draw the complete Lewis structure and specify the direction of the dipole moment. So remember, when you're dealing with polarity, you always have to have the proper, right? You have to draw the complete molecular structure, right? You have to draw the three-dimensional shape, right? So for this first one here, right, here's our complete Lewis structure. It's a tetrahedral molecule. It's sp3 hybridized, all that kind of good stuff, right? So once you draw the proper Lewis structure, you got to, it asks you to specify the dipole moment. Remember, we draw our vector arrows, right? They're pointing towards the chlorines here because chlorine is more electronegative than carbon, right? So we've got a negative charges building up here at the chlorines, right? And remember that these are vectors, so they're additive, right? And so the overall dipole would be like this, kind of pulling in between the two chlorines there, right? The bond angle in here, everything is 109, right? Idealized at 109.5, right? So the green vector arrows are not pulling in opposite directions, right? They're pulling, at 109 degrees from each other. So the overall red vector arrow there is how the dipole will go. Okay. So HCN, right? There's our Lewis structure for HCN, right? We've got right? Technically, carbon slightly more electronegative, right, than hydrogen. So you could have drawn this in here. That's why I'll put air quotes around that. Remember, we assume for this class that hydrogen and carbon have equal electronegativity. So then there's our vector arrow for this, and this is the one that you're looking for, right? You got a pretty strong pull towards the nitrogen there, right? So we got our partial negatives and our partial positives here, okay? All right, we got H2O2, right? We've got a set of sp3 hybridized oxygens here, right? So each one of these is going to be, oops, I didn't mean to draw that, excuse me. So we've got a set of sp3 hybridized oxygens here. So you could have drawn something like this, right? Where you put some, let's put a hydrogen back here, you put a lone pair, right? We'll put a hydrogen here and a lone pair, right? So you could have done something like this, right? Although there's different variations of this also, right? I think if we try and simplify this as best we can, right? That might be the best way of drawing it, something like this, right? The point I'm trying to get is that there is three-dimensional shape with this, right? It's not a planar molecule, right? It's not a planar molecule. So we're pulling towards our oxygens, right? The lone pairs, all this kind of stuff. So overall, the net dipole is going to be kind of pulling up in that direction there, okay? Remember, if you're asked, is a molecule, are the molecules polar, draw the overall dipole, right? We have to look at a three-dimensional shape, and that's the whole point, okay? Okie dokie, draw all major contributing resonance structures. Okay, so let's zoom in here. So we see a lone pair, and we're next door to a pi bond. Let's get a different color here. So we're going to do this, right? This, okay? So let's see what happens. We got 1, 2, 3, 4, 5, 6. Okay, so, oops, I accidentally started upside down, I guess. Let's keep it the same as much as we can, right? So there's our original. We turned our lone pair into a pi bond, and we turned our pi bond into a lone pair, and we still have our pi bond over here, right? And that's it, right? That's it. We cannot do anything else, right? If we try and do that arrow in purple, right? If we try and do that arrow in purple, here's where we end up with, right? Let's take a look. And you're like, yeah, that looks nice, right? I like that. Well, take a look, right? This carbon in red here, it has two hydrogens on it, right? It has two hydrogens on it. So you can't do that arrow in purple, right? You can't do that, right? You're over octating the red carbon there. Okay? So we really only have one resonance structure here, and that's it. Okay? This guy over here is too far away, right? It's not next door to anything, right? It's not next door to anything. So that's it. We're done. Easy peasy, right? Okie dokie. Here we've got another one. Let's start out by doing, we'll use blue. Blam. All right. So we got our buddy nitrogen right here. Right, we made bond in blue right there and moved our positive charge there. Good. All right. So here's our nitrogen. Now we made our bond in red. Bond in blue is still over there. And our consequence is that we now have a positive charge on our nitrogen. Right? So here we've got two resonance structures. Great. All right, there's the second page. If you guys need to pause this and copy down what you need to, and we'll move on. All right. So not going to be too much writing on this, so I'm just going to be talking to you guys a little bit, so take your notes as you want to. Let me give you guys the answers here first, right? So answers of which ones are the stronger acids, right? It's going to be those right there, right? So those are going to be your stronger acids, and each one of them has a different reason, okay? Now, remember, or one way to approach this is, if I'm asking you which one's the stronger acid, well, make them both act like an acid, right? Make them both act like an acid, and, right, they get rid of their most acidic hydrogen, all right, right? And then you analyze both of these and say, okay, well, which one is the better, right? Which one has the better handling of that negative charge? So in both cases, we have an oxygen with a minus charge, so we can't say anything about size, or we can't say anything about there being a difference in size or hybridization or any of that kind of stuff, right? There's not really any difference in that. The difference is resonance, right? We can draw a resonance structure for this molecule, right? I'm not going to draw all of them, although I would highly suggest that you guys do, right? We could draw, wow, I just made a huge mistake. This is why I don't like to, I wish I could edit this a little bit better, but sorry. So back up for just a second. Sorry about this. There it is, okay? So we can draw resonance structures. All right. So we can draw resonance structures. Now I will go through and draw the rest of them for you, so because of that confusion there, right? So we can continue to go through and draw more resonance structures for all this. And then, as I'm doing this, we will ask the important question. Right, yellow here, black there, all right. Minus charge, and we'll do one more. Let's do purple. Okay. All right, so we made this one purple. Now purple is here. This one was red, and this one was yellow. All right. Okay. So here are all the resonance structures. Right? Here are all the resonance structures for this. What is the consequence of this? Well, remember, right? If we can spread a charge out, so we spread our charge, right? We spread our charge, right? It's a delocalized negative charge, which makes it a weaker base, right? Right? And a weak base comes from a stronger acid. Right? So a weaker conjugate base comes from a stronger acid. There is no way, right? delocalization. There it is. Okay. There is no delocalization on that oxygen right there, which means it's a very strong base. And strong bases come from weak acids, right? So the approach here, I was asking us to talk about resonance and discuss what that resonance does, right? We're spreading our charge around, right? We're spreading our charge around. All right, so, sorry. Let's take a look here, right? Same thing. Make them both act like acids. There's that. Okay, and there's that. There is a difference in electronegativity. There's also a subtle, slight difference in radius. There's no difference in hybridization, right? So the difference here comes from electronegativity, right? Oxygen is more electronegative, so it's better at stabilizing that negative charge, right? It's better at stabilizing that negative charge, right? It can stabilize that minus charge better, right? Which makes it a weaker base, and weaker bases come from stronger acids, right? So I was looking for discussion about electronegativity and how that helps stabilize that minus charge, right? This one was probably the trickiest one here, though. More of the same. All right. Okay, we made them both act like acids. Yes, oxygen is more electronegative, right? It is more electronegative, but this has larger radius. And it just so happens that in the same family, right, sulfur is below oxygen on the periodic table. The larger radius is going to dominate in terms of properties with respect to acidity. And the reason why is because if we have a larger radius here, okay, then we can spread that minus charge out, right? We have a bigger surface area, right? If you kind of want to think about this, right, you have a larger sphere to spread that minus charge out. And again, that's just a stabilizing effect. The more we can spread out a charge, the more stable it is, if we want to think about it on that, right? So larger radius means a weaker base, and weaker bases come from stronger acid, right? So the discussion here should have been about radius and how that spreads the minus charge out. Okay? So I'll zoom out here just so you guys can see everything, and if you need to. Okay, last page. How many sp3 hybridized carbons are in this molecule? Well, we got that guy right there, and we got that guy right there. Right? So we got 2. How many sp hybridized? Well, we got that guy right there. So we got one of those, and how many sp hybridized do we have? We got a big old zilch. Okay. Now, how do you recognize this? How do I know this so quickly? Right? Well, what I'm looking at, right? Right? I'm looking at how many things are bound to my carbon, right? If you've got four single bonds to a carbon, right, that's an sp3 hybridized carbon. If you've got, a double bond, if you've got a double bond to a carbon, right, and then 2 single bonds, right, it's a trigonal planar carbon, that's an sp2 hybridized. And sp hybridized carbon atoms are, with triple bonds. Right, so I'm just looking at the bonds, I'm looking at the hydrogens, I'm showing you guys the trick that we did in class there, right, the bonding regions, right, I'm counting bonding regions, okay. And the last thing is we need to draw resonance structures, right, any significant resonance structures, where there just happens to be only one that we have to deal with here, right, so let's draw this, let me draw this a little bit better. All right. Okay, there's this. Now, to be able to draw, well, I guess I could put that in there. Okay, so to draw a resonance structure, we're looking for lone pairs next to open orbitals, lone pairs next to pi bonds, right? Well, the only thing we can do, right, this is the only place where a lone pair is next door to a pi bond. So our answer for the resonance structure is going to look like this. So we got yellow bond, right? We'll just fill these in here real quick. Boom, 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 boom. Okay. All right. And these didn't go anywhere. Right, these didn't go anywhere. That's all we can do, right? That's it. Okay. Anything else is going to be a not useful resonance structure, right? We will cause things with negatives next to negatives or 2 minus charges, right? We're going to just start creating ridiculous things, right? Now you could, well, now actually, you know what? We'll just end it at here, okay? So that's the only resonance structure that's really of note for us, although you guys will learn more about amides when you get to the second semester of organic chemistry. All right. There we go. That's the end of exam 1. If you guys have any questions, just drop me an email or see me after class or before class or whatever it is.